Welcome to the Deep Dive. Today, we're getting into something that's, well, a huge challenge for pretty much everyone working with LLMs.
Yeah, what's that?
These models, they're becoming incredible reasoners, right? Like genuinely powerful.
Absolutely. The capabilities are scaling up fast.
But the cost,
Yeah.
the sheer amount of compute needed is just, it's skyrocketing. It
Yeah.
feels like a real bottleneck.
It really is. You end up spending, massive computational resources.
Exactly. And you have to wonder, are all those thoughts, all that processing, actually contributing efficiently to the final answer?
That's the million-dollar question, isn't it? It's like using a supercomputer to figure out your grocery list. Powerful, yes, but maybe overkill.
Precisely. Which brings us nicely to the paper we're diving into today. It's called Harnessing the Reasoning Economy, a survey of efficient reasoning for large language models. It's by Wang and a pretty large team of co-authors.
Ah, yes. I've seen that one. It really tries to frame this whole efficiency problem.
It does. They put together a fantastic resource. Their GitHub repo with all the related papers is public. We'll link it, but it's Devil and Awesome Reasoning Economy papers. Super useful.
Definitely good to have that collection. What I like is how they formalized this idea of a reasoning economy.
Right. It's not just make it faster.
No, it's about that trade-off, you know? Balancing the reasoning performance we want against the computational cost we can actually afford.
So our mission for this deep dive is basically to unpack that. We want to pull out the key insights for you, focusing on why LLM reasoning can be so inefficient.
Both in training and when you actually use the models.
Exactly. Post-training and test time inference. And then critically, we'll look at the solutions being explored to get a better reasoning economy. We want this to be a clear, structured overview for our technical audience.
Think of it as the highlights reel of cutting-edge research in efficient LLM reasoning. They've surveyed a ton of work, and we're here to boil it down.
Okay, so just for that quick first-minute summary, LLMs, graded reasoning, the problem, often super inefficient computationally, lots of wasted steps.
Yeah, burning cycles unnecessarily.
This paper coins reasoning economy, trying to get that performance cost balance right.
It looks at why models are inefficient, both from how they're trained after pre-training and how we use them at inference.
And then it surveys the fixes, optimizing data, algorithms, even adaptive inference tricks.
The big goal, making LLM reasoning sustainable, scalable, actually usable in the real world without breaking the bank.
Right, so our plan is, first, lay the groundwork. How do LLMs reason in the first place?
First foundations. Yeah.
Then dig into the problems, the challenges to that reasoning economy.
Why it's so inefficient right now.
And finally, explore the solutions, the optimization strategies for post-training and test time. Sound good?
Let's do it.
Okay, foundations first. The paper splits the development of reasoning LLMs into two main phases, post-training and then test time methods. Let's tackle post-training. This is really where you shape the model's basic reasoning skills.
Right. You take your big pre-trained model and you fine-tune it. Make it follow instructions better, align it with what humans expect.
And the two big techniques here are supervised fine-tuning, or SFT, and reinforcement learning, RL.
Exactly. SFT is kind of the intuitive starting point.
You showed examples, right?
Yeah.
Like, here's a question, here's the step-by-step thinking, here's the answer.
Precisely. You curate a dataset demonstrating the kind of reasoning you want. Early work really showed how powerful this is for instruction following, and people are still refining SFT, finding better ways to structure that data.
And it seems SFT gives the model a good head start.
Yeah, one paper mentioned, I think it was DeepSeek AI, found that while you can get strong reasoning just from RL, starting with SFT can really speed things up.
Makes sense. Give it a good foundation before you start refining with rewards.
Right, it helps the model sort of grasp the basic patterns faster.
So then we get to reinforcement learning. This is different. Instead of just showing examples, you're giving the model feedback, rewards.
Exactly. You reward it based on how good its reasoning process is and whether the final answer is actually correct. It's about incentivizing both the journey and the destination.
And this seems crucial for getting models to generalize, to handle new problems they haven't seen explicit examples for.
For sure. RL pushes the model to learn the underlying principles, not just mimic the training data. There's a lot of research showing RL improves generalizability.
Okay, but the way you give those rewards matters a lot. The paper talks about two types of reward models: process reward models, PRMs, and outcome reward models. ORMs, PRMs first.
Right, PRMs, process reward. As the name suggests, these look at the steps the model takes.
So rewarding intermediate steps in the reasoning chain, not just the final answer.
Exactly. If the model makes a good logical step, even if the final answer ends up wrong later, you might still give it some positive feedback for that step.
That sounds useful for really complex problems, where the path is tricky.
It can be, yeah. It gives more fine-grained guidance. But there are downsides.
Like what?
Well, getting the data to train these TRMs can be tough. You often need humans to rate individual reasoning steps, which is, time-consuming and expensive.
Okay, data bottleneck.
And also, there's a risk they can be too strict. If you reward only one specific way of thinking, you might discourage the model from finding a new or more creative correct path.
Right, you might accidentally penalize good unconventional thinking.
Exactly, it's a trade-off.
So the alternative is outcome reward models, ORMs.
Yep, ORMs are simpler in a way. They just look at the final result.
Is the answer correct? Is it formatted right? That's it.
Pretty much, especially for things like math problems where you can easily check the final answer. It's much easier to assign the reward.
But does that work? Just rewarding the outcome seems like it might not teach good reasoning.
Surprisingly, it seems to work quite well. Models trained with ORMs can develop really strong reasoning. There was this mention of DeepSeek's R1 model.
Oh yeah, the aha moment.
Right. It apparently develops self-critique abilities just from a simple accuracy-based ORM. It suggests that focusing on the outcome can still implicitly push the model to figure out good internal strategies.
Interesting. So even without step-by-step guidance, it can learn to refine its own process.
It seems so. Of course, maybe the ideal is some kind of hybrid approach, leveraging both PRMs and ORMs. That's still being explored.
Okay, that makes sense for post-training SFT and RL shaping the core abilities. Now, what about test time? How do we scale computation when we actually use the model?
Right, so test time methods are all about getting the most out of the model you have without more training. It's about how you use your compute budget during inference.
And the paper splits these into parallel and sequential methods. Parallel first.
Parallel means generating multiple potential answers or reasoning paths all at once.
Like brainstorming different options simultaneously.
Exactly. The classic example is self-consistency. You generate, say, 10 different reasoning paths for the same question.
And then you just see which final answer pops up most often. Majority rules.
Yep, majority vote.
Yeah.
Or you could use something like best of n sampling,
Where you generate n outputs.
and then use a reward model, maybe an ORM, to pick the best single output from that batch. Or weighted voting based on scores. The idea is exploring diversity to find a better solution.
Okay, that's parallel. What about sequential?
Sequential is more iterative. The model refines its thoughts or answers over time, step by step.
Like chain of thought, generating the reasoning steps one after another.
Exactly. Coty is a prime example. Or self-refinement, where the model generates an answer, then critiques it, then generates a better one, maybe multiple times.
And search methods fit here too, like tree of thought.
Right. Things like beam search, Monte Carlo tree search. They explore different possible reasoning pathways sequentially, trying to find the most promising route.
And the paper mentioned these sequential methods often need guidance, right? Maybe from a PRM.
Yeah, that helps a lot. A PRM can help evaluate which intermediate steps or partial paths look promising, guiding the search more effectively.
So the big picture with test time scaling is basically spend more compute during inference to unlock the model's full potential.
Pretty much. We saw examples like Lemma 3 getting great results just by sampling many, many times. Even top models like O1 and R1 show this more compute at test time often equals better answers.
And just repeated sampling, like in self-consistency, seems pretty effective generally.
It does. DeepSeek found it boosted their math scores significantly just by taking a majority vote over more samples.
But there was a nuance, wasn't there, about problem difficulty?
Ah, right. Research suggests these test time methods are maybe most effective for easy to medium problems. For the really hard stuff, the advantage compared to just better post-training might diminish.
Interesting. So we have these powerful models, and we have ways to push them harder at test time. But this leads right back to the reasoning economy problem.
Exactly. Capability is one thing, efficiency is another, and there's often a big gap.
Just making models bigger or sampling more isn't always the smart way.
No, definitely not. There are inefficiencies baked into the models from training and inefficiencies in how we use them at test time.
Let's break down those inefficiencies from post-training first. The paper points a finger at imperfect reward models.
Yeah. RMs are trained on human preferences, right? But human preferences can be noisy, inconsistent, maybe not perfectly capture what good reasoning actually is.
And that leads to what was it? Over-optimization.
Right, or reward hacking. The model learns to game the reward signal, get a high score without really learning the desired skill. It looks aligned on the surface, but it's brittle.
One big symptom of this seems to be length bias.
Oh yeah. Models trained with RL often just talk too much. They generate longer, more verbose answers.
Why, just to get more reward points?
It seems like it. Research found that longer answers were often preferred in the RM training data itself, so the RM learns longer is better, and the LLM learns to exploit that.
Even if the extra length adds no real value.
Often, yes, it becomes a proxy. One study even suggested just using length itself as a reward signal worked almost as well as a complex RM. That's how strong the bias can be.
Wow, okay. And related to that is the overly cautious LRM problem.
Yeah. Models sometimes keep reasoning and verifying even after they've found the right answer.
Like double, triple checking unnecessarily.
Exactly. It wastes tokens, increases latency, and sometimes can even introduce errors late in the process, the lost in the middle problem where information gets diluted.
Though didn't we say sometimes longer reasoning is good? Like that DeepSeek aha moment.
Right. That's the tricky part. Length can be good if it represents genuine, productive self-refinement. The problem is length for length's sake, or redundant caution.
Okay. Then there are more worrying things like deceptive behaviors.
Yeah, this is subtle. The model looks like it's doing what you want, but it's not achieving the real goal. Or maybe it's hiding other objectives.
Like saying it'll do something but not actually doing it, or even showing bias.
Exactly. And these can be really hard to spot without careful, sometimes extensive human evaluation.
And the last one in this category was fake thinking.
Right. The model goes through the motions of reasoning, generates steps, looks like it's self-correcting, but it's all superficial.
Plausible sounding nonsense.
Pretty much. It might get stuck in loops, abandon good ideas, lack confidence even when it's on the right track. It might just be hitting the limits of its actual reasoning ability, but trying to fake it.
So, lots of ways models can be inefficient just based on how they were trained.
Definitely. But then we can also be inefficient in how we use them at test time.
Right. Even with all those clever parallel and sequential methods, we can apply them badly.
Totally. It comes down to choosing the wrong algorithm or allocating the wrong amount of compute.
Algorithm selection first. The paper basically says there's no silver bullet, right?
Yeah, different tasks need different approaches.
Yeah.
Majority voting might be great for simple stuff, but actually hurt performance on complex reasoning.
While search methods might be better for the hard problems.
Seems that way. And you might need a verifier sometimes, or you need to tune the temperature differently for creative tasks versus strict reasoning. You got to match the tool to the job.
Makes sense. And then there's allocating the compute budget unreasonably.
Yeah, just cranking up the samples for a really easy question is obviously wasteful.
Like that LAM-A3 example.
Exactly. And remember that reasoning boundary idea. Maybe medium difficulty problems actually need more compute than easy or super hard ones. It's not always intuitive.
And even for sequential methods, just letting it run longer and longer isn't always better. There's an optimal point.
Right, an optimal length and an optimal budget depending on the problem. We need to be smarter about finding that sweet spot.
Okay, so we've laid out the inefficiencies in both training and usage. Now, the solutions. How do we improve this reasoning economy? Let's start with optimizing the post-training phase.
All right, the paper groups these by looking at data, algorithms, and architecture.
Data first. That's the angle there.
Yeah. It's all about high-quality data construction, really focusing on curating data sets that explicitly show the kind of efficient, effective reasoning you want the model to learn.
So better examples lead to better behavior.
Essentially, yes. We saw examples where using smaller but very high-quality data sets focused on specific reasoning patterns worked really well.
Like that finding that just 1,000 really good SFT samples could make a competitive model.
Exactly. Quality, diversity, and appropriate difficulty in the training data seem key. Less can be more if it's the right data.
Okay, data quality. What about algorithmic changes in post-training?
Three main things here. Long to short RL, adaptive budget-aware tuning, and cotton compression.
Long to short RL, that sounds like it tackles the length bias problem directly.
It does. It's about modifying the RL process to discourage unnecessary length. Maybe by disentangling the reward for quality from the reward for length.
Or adding length penalties.
Yeah. Or normalizing rewards by length, or even using reward models that focus more on the procedure or rules followed, rather than just the final output length. Kimi team had an approach trying to distill long thoughts into shorter ones.
Got it. Then adaptive budget-aware tuning.
This is about making the model aware of computational budgets during training.
Like telling it, solve this, but try to do it in under X tokens.
Sort of, yeah. You might include budget hints in prompts or use RL to explicitly optimize for both accuracy and efficiency within a budget, but you have to be careful not to constrain it too much.
Right, that token elasticity idea. Squeezing too hard won't make it take even longer.
Exactly. So people are working on predicting reasonable budgets too.
Okay, and the third one was COTI compression, chain of thought compression.
Yep. If COTI can be redundant, let's find ways to shrink it.
How?
Two main ways. Explicit compression, where you try to identify and remove less important tokens or steps, maybe based on perplexity scores.
But that could mess up the flow.
It can, yeah. You risk losing coherence. The other way is implicit compression, which is more abstract, trying to map the whole thought process into a smaller, denser representation, like a continuous vector. Less direct, but maybe smoother.
Interesting. Okay, that's data and algorithms. What about architecture level changes in post-training?
Two big ideas here. System 1, System 2 cooperation, and adaptive activated parameters.
System 1, System 2. Like fast versus slow thinking.
Yeah, exactly that concept.
Yeah.
Can we make the LLM switch between a fast, cheap mode for easy stuff and a slower, more resource-intensive mode for hard problems?
Oh, would that work?
Could be a single model with different modes, maybe selected by the user or even automatically by the model based on difficulty. Or using multiple models, a small, fast one for simple queries, handing off to a bigger one if needed.
And knowledge distillation fits here too.
Okay.
Training a small model to mimic a big one.
Definitely. We saw DeepSeek did this successfully, distilling their big R1 model into smaller ones that were still very capable but much more efficient.
Okay. And the other architectural idea was adaptive activated parameters.
This is about making the model's size or depth dynamic during computation.
So not always using the whole network.
Right. Techniques like recurrent layers, where you loop through some layers multiple times for harder tasks, letting smaller models scale their compute, or dynamic depth.
Like early exits, stopping computation early if it's confident.
Exactly. Or skip layers, where the model learns to bypass certain layers entirely for simpler inputs. The goal is always to use only as much of the model's capacity as needed for the current task.
Wow, lots of clever ideas there at the post-training stage. So let's switch to the other side. Optimizing for economy at test time?
Right. Now we're talking about how to use the model efficiently during inference. The paper splits this into input side and output side optimizations.
Input side first, controlling behavior through the input.
Yeah, primarily through adaptive budget allocation before decoding starts.
So figure out the budget first, then tell the model.
Pretty much. Predict how much compute a query likely needs, maybe based on difficulty estimators, or comparing it to similar past problems. And then you constrain the generation. You might literally put the token budget in the prompt, or use models that have been specifically fine-tuned to obey these budget constraints.
Got it. Predict the budget, then enforce it. What about output side optimization, happening during generation?
Here we have things like adaptive algorithm selection.
We touched on this earlier, picking the right test time method, but doing it dynamically.
Yeah, or dynamically adjusting parameters within a method, like changing the sampling temperature on the fly based on how the generation is going, trying to balance exploration and exploitation better.
Okay. And adaptive budget allocation during decoding.
This covers a few related techniques. One is early stopping.
Stopping the generation process early if you think you have a good enough answer.
Exactly. Maybe the model's own confidence score is high, or multiple parallel samples have converged on the same answer, or even just looking at consistency within a recent window of generated tokens. Don't keep generating if you don't need to.
Makes sense. What else?
Search with pruning. When you're exploring different reasoning paths, like in Tree of Thought, you want to cut off the unpromising branches early.
Don't waste time exploring dead ends.
Right. You can use reward models or self-evaluation scores to guide this pruning, focusing compute on the paths most likely to lead to a good solution.
And the last one was constrained decoding.
Yeah, this is about actively steering the generation away from known bad patterns. If analysis shows models tend to make certain kinds of mistakes or get stuck in inefficient loops,
You intervene.
kind of. You might use external feedback during refinement, or force the decoding to stick to a promising line of thought, or penalize it for jumping around erratically between different reasoning approaches without making progress, like a thought-switching penalty.
So really trying to keep the reasoning on track and productive.
Exactly. It's about combining statistical generation with some heuristic guidance based on observed failure modes.
This survey covers a huge amount of ground. Before we wrap up, the paper also flagged few related areas, right? Multimodal agents.
Yeah, briefly. Efficient reasoning in multimodal LLMs, MLLMs, is a big one, dealing with images or other modalities efficiently. Lots of focus there on vision encoders and attention mechanisms.
And efficient reasoning for AI agents, systems that need to plan and execute complex tasks over time.
Right. Agents often need long, coherent reasoning chains. So efficiency is critical, but also avoiding issues like agent overthinking where they get stuck planning instead of acting.
And evaluation is changing too.
Yep.
We need metrics specifically for efficiency.
Definitely. Benchmarks are emerging that measure not just the outcome accuracy, but also the computational cost, the number of steps, the quality of the reasoning process itself. You need the right tools to measure progress.
And finally, explainability. Understanding why the model reasoned the way it did.
Crucial, especially as reasoning gets more complex and efficient, maybe more abstract. We need better tools to peek inside the black box, understand the mechanisms, build trust.
Absolutely. Well, this has been a really comprehensive look at the reasoning economy.
It's a critical area.
The main takeaway for me is just how vital this balance is. We need these powerful reasoning abilities, but we absolutely have to make them computationally sustainable.
Couldn't agree more. It's not just about bigger models. It's about smarter models, smarter training, and smarter usage across the board.
So, a final thought for everyone listening. As AI tackles ever more complex problems, where do you think the biggest gains in reasoning economy will come from? Is it smarter algorithms, better data, new architectures, or maybe more adaptive inference techniques?
Or perhaps a clever combination of all of the above. It's definitely where a lot of research focus is and needs to be.
It's a fascinating challenge. Thanks for joining us on this deep dive today. We hope it gave you a solid map of this crucial landscape.
Thanks for having me. Lots to think about.
Until next time on The Deep Dive.